Hello students, so today we will be learning about the rectangular waveguide system, and in a last class we have seen the parallel plate system where we try to find it out the different field components, having some assumptions here. So now here we'll be taking the practical rectangular waveguide system, and definitely those assumptions what we have taken last time will be not considering here actually, because we'll be trying to find the field component for this practical rectangular waveguide system. So I'm going to make first the waveguide, okay, and how it looks actually, then we'll be finding the its field components. Fine, so let me draw. Just a minute. Okay, so let's say this dimension is a. Just a minute, I need to stop it. This dimension is a and this dimension is b. Fine. Okay, now mark the axis here too. So this is x-axis, okay, and this is y-axis, and this is z-axis. Fine. Of course, this waveguide may be empty or may be having some media. So let's say mu and epsilon. Fine. Permittivity and permeability, okay, we can define. Now considering this waveguide system along the z direction, it is infinitely long. Fine. With this in this analysis actually, and later on we'll be taking the practical scenario, okay, because we are going to close that in a z direction, so making a cavity also. So there is a application of this rectangular waveguide in a cavity we'll be learning after this. Right now, so this rectangular waveguide system can support the T and TM, both the modes. Fine. So this can support TE or TM, both the modes. It could be supported by this rectangular waveguide system. Now another important thing is here that this is made with a single conductor system, means all these walls, okay, you can see here, this is made of metallic, or we can assume the PEC, perfect electric conductor here. Fine. So because this rectangular waveguide is going to support both the modes, fine, and this is a single conductor system. So let us first try to define all the components for the T mode as well as the TM mode, and later on we'll see also that different parameter what we already checked in case of the parallel plate system, like the cutoff frequency, okay, beta, wave impedance, and other properties too. Fine. So I'm going to start here with the rectangular waveguide for TE mode. Okay, so when we have the TE mode, okay, then we will be analyzing here this rectangular waveguide system. Fine. Now from the previous classes actually, we can recall certain things actually to derive these field components for the TE mode system. So we are aware about this differential equation, the second order differential equation. I believe you can recall it. Dou square is z xy dou y square plus kc square hz, of course x and y is equal 0. Fine. So here you can see this is a longitudinal magnetic field function for the TE mode. Okay, within the rectangular waveguide system must satisfy actually this second order differential equation. Fine. And we know about this Kc actually. It was defined as previously, this is k square minus beta square. Okay. Now if you recall actually the previous class, and there actually we studied the parallel plate waveguide system, where the separation between two plates was very small as compared to the width of the parallel plate system. Now with this assumption actually, so we neglected the field variation, but here actually we cannot do that particular thing. So here this Hz, okay, the longitudinal field component, okay, if you know, you can solve this differential equation actually for this things. So earlier we saw this Hz is a function of a single variable actually. Now here we have the x and y, two variable will be existing here. So what we will be doing here, solving this differential equation by we are going to use the method of separation of the variable technique. Okay, so from there actually, yes, we can solve this differential equation. So now assuming the solution actually in the form of Hz is a function of xy, is x is a function of x, capital Y is a function of small y. Right? So we are assuming here this is solution form, correct? Now if it is fine, correct, we can put these things in a previous partial differential equation. Okay, and the moment you are putting this equation, this solution actually, these things, the form of the solution, so you may write like this, that previous partial differential equation, this is hopefully this is acceptable to all. Fine. So yes, we are replacing Hz is a function of xy with x is a function of x, y is a function of y. Fine. Now we can do one more step here. If you can divide this whole differential equation with x, y, okay, and finally you can write a different form and could be more like clear, okay, in terms of the solutions. So it would be 1 upon x, the function of x, fine, and this is 1 upon y, and of course d square y dy square plus kc square is equal to 0. Fine. Now if you see this equation actually clearly, you will find that that first two terms, these two terms, okay, these are each depends only one variable. Okay, you can see this depends upon the only one variable. Fine. So in order to satisfy, okay, for every x and y within the waveguide, so these two terms must be equal to the constant. Fine. So what I'm saying that this term, okay, is equal to some constant, let's say kx. Okay, this is a second order, so making a square here, and this is ky square. Fine. Okay, so we may write like this. Okay, now if this is fine, so we can write this equation like this. How we can write? 1 by x is a function of x, d square x y dx square plus kx square is equal 0, or what you can say is equal minus kx square, and this could be further rewritten as d square x dx square plus kx square x, the function of x is equal 0. Okay, so here you can see this is a one differential equation we have. In a similar sense, actually, for y you can write another second order differential equation here. So I'm writing both actually these things. So the last one was dxx over dx square plus kx square xx 0, and the second one is d square y d y square plus ky square y. Fine. And here how we can do these things, this will be kc square is equal kx square plus ky square. This is the separation equation. Fine. So what we can do after that, actually, you can see here the similar situation we got, like we made for the parallel plate waveguide system in the last class, and considering the gap between these two plates is very small, the same situation we can see. This is completely depends upon the only one variable x or y. Fine. So it is easy here to write the solution, a general solution for this. Okay, so I'm writing the general solution for these two equations as x is a function of x, a sine kxx plus b cos kxx. Fine. And for this is y, the function of y, c sine ky y plus d cos ky y. Fine. Okay, so it means if you multiply these two, actually, okay, you will be getting your original hz is a function of xy. Okay, what I'm saying that hz is a function of xy is like nothing but we started like this. Fine, with separation method. So you can write like this: a sine kxx plus b cos kxx, and of course c sine ky plus d cos ky. Fine. Okay, now this is one thing. So yes, we can going to use this. Okay, taking the next page. Okay, so this was the thing. Fine. Now finally we can write the longitudinal magnetic field component, okay, overall as hz is a function of xyz. Fine. And the same thing, okay, this one. Okay, fine, is equal to this, and of course a term we should not forget, e to the power minus j beta c. Fine. So this is our longitudinal magnetic field component overall. Fine. So how we started the separation method, okay, we segregated, then we recovered these things once again. Now we have here the hz component, and once you have the hz components, yes, you can find the other field component associated with this mode for this rectangular waveguide. Fine. So what we need to do actually, we need to write the boundary condition first here. We need to define, because the structure is very simple here and we can write certain boundary conditions here. How we can write? Let us check. So the boundary conditions could be written as here Ex, okay, the x component, which is x comma 0 comma z. Fine. Means I'm talking about the horizontal walls. Fine. First, okay, so this is the bottom one, and for the top one this is Ex xb z, and this should be 0 because, okay, we are considering this is a PEC, made of PEC. Okay, so this is for what? This is horizontal walls. Fine. Similarly, you can also write for the vertical walls the EY component as 0 y z is equal to EY a y z equal to 0. So this is for the left hand side and this is for the right hand side. Okay, and this is for vertical walls. Fine. Now once these boundary conditions are clear actually, okay, so you can apply those boundary conditions, but where you will apply actually, you're supposed to have this Ex and Ey component. And if you recall from the previous classes actually, we already derived the Ex component in terms of the longitudinal magnetic field component as Ex is equal to minus j omega mu divided by kc square dou hc over. Can you recall it? Okay, so this was the thing. Now we have hz here. Okay, we have hz here. You can differentiate with respect to y. Okay, and then after you can impose the boundary condition as we written here. Fine. Okay, and similarly you can also write Ey. Okay, what was the thing? J omega mu over kc square dou hc over dou x. Fine. So you're supposed to differentiate, okay, that longitudinal component with respect to x. Fine. Okay, so this is quite clear. Fine. Now I'm just copying here this boundary condition because we will be utilizing. Okay, and yes, so I will be using this Ex and Ey component imposing these boundary condition. Fine. So okay, so let me just paste these things. Yeah, so this is the boundary condition. Fine. Now you're supposed to differentiate that part, and the moment you will be differentiating, so you will be having the Ex as, okay, I'm writing the final one, minus j omega mu over kc square ky a sin kx x plus b cos kx x, of course c cos ky y plus, no, this is minus d sin ky y. Okay, because this thing you are differentiating with respect to y, the rest will be constant for this. Fine. And of course we should not forget e to the power minus j beta z. This is one thing. Now if you impose this boundary condition to this equation, so you can conclude like that when you are imposing Ex is equal Ex the function of x 0 z. Okay, so the moment you are putting this, so y will be 0. Fine. So if you're putting y, this will be, this whole term will be alive, where this term will be 0. Fine. This term will be 0 completely. fine. But before that actually the other terms are also there, like this a sin x and b cos x. So better to write first ey, okay. Will be imposing the boundary condition. Maybe we will be getting some additional outcomes. Those can be utilized here the in ex, fine. So what I'm doing, the previous equation, that is ey, okay, I'm differentiating, so we can write ey as, just a minute, fine. So ey you can write as j omega mu over kc square kx, of course a sin kx, and here you differentiated with respect to x, so this will be minus b sin kx x, and the second term will be constant for this, so we can just repeat like here, sin ky y plus d cos ky y, of course e to the power minus j beta j, fine. Now recalling boundary condition ey 0 y z is equal 0, okay. So the moment you are putting these things here actually, so what happened that there this term will be 0, okay, this term will be 0, fine. So what you can conclude actually here, and what about the other terms are here, this is y, this is y, this is z, okay, and we are exploring this x component here, which is 0, of course, fine. Oh sorry, this is just let me correct it, this is cos, okay, this one is a cos, fine. So yes, yeah, that is why I was just confused that how it will make it 0 overall. So here if you see, okay, this will be 0, fine, this term will be 0, but the idea is here we require the whole ey will be 0, fine. It means what actually, we can conclude that if, because we cannot say about the cos kxx, so definitely this constant will be 0, so there is the one outcome here, that a will be 0, one thing. Another point is that if we are recalling ey a y and z is equal 0, fine. So right now a is 0, fine, a is 0 with us, fine, okay, and here in place of x, okay, you are replacing this a, fine. So again actually the moment you are putting here these things, okay, this is kxx and this is kxx, in place of x you are putting this a, okay, and to satisfy this equation actually, okay, to satisfy this equation definitely, okay, the argument which is kx and in place of x you will be a, should be the m pi, where m is 0, 1, 2 and also these things, fine. I hope this is acceptable to all. The overall aim is to make these because we are considering the things at the boundary, okay, or at the edges actually, correct, these boundary conditions we are trying to satisfy. Now in a similar way actually you can use this ex equation, and again you can utilize these boundary conditions, okay, as ex x 0 z is equal 0, fine. So for this actually it is again, if you try to put here this equation, so you will find that you have to make c is equal to 0 compulsory, otherwise this equation will not be satisfied, Fine. Now the last one is that ex, x, b and z is equal 0. So this one will give you the in the same way ky b is equal n pi. Again n is equal 0, 1, 2 and up so on. Fine. So right now we concluded like that with this boundary condition that a should be 0, c should be 0 and the kx a is equal multiple of pi and ky b is equal to n pi. Fine. So with this information, actually once again we can collect all this information and we will be putting in hz. Fine. So how it look like if we are using this information, and the informations are, I am writing once again, a is equal 0, c is equal 0, kx a is equal m pi and ky b is equal n pi. Of course n is starting from 0 to 0, 1, 2, 3 like that. Fine. So hz component will be what? Okay, so recall that hz component. Okay, yes, this is the hz component. So here this a and c will be 0, so you left with these terms only. Fine. b cos kxx and d cos kyy. Fine. So these terms will be there. So it will be b into d into cos m pi x a cos n pi y by b e to the power minus j beta z. Now one more thing, like if you see this is constant actually, so let us rename it these things as a new one as a m n. Fine. So basically this constants b and d we combined into one constant named as a m n. Fine. Because definitely these constants will depend upon this m n n also. Fine. Now having this information, okay, again you can recall the ex and ey, correct? These all the transverse component you can write once again. Fine. So I'm writing here all the transverse component, okay, because right now we have hz here. Fine. And we can completely write these transverse component as ex, the first component will be the function of x, y, z is equal to j omega mu n pi. Please try to differentiate once again, take from these things, okay, and yes, and try to verify what I'm writing here. Fine. So kc square b a m n cos m pi x over a sine n pi y over b e to the power minus j beta z, and of course ey is a function of x, y, z is minus j omega mu m pi divided by kc square a m n sine. You need to verify all those equation by differentiating. Hopefully you can able to do this differentiation. It is quite easy. You can verify n pi y over b e to the power j beta z. Fine. And similarly you can also write the transverse magnetic component also, which is hx as minus j beta, okay, writing directly the outcome, j beta m pi over kc square a m n sine n pi x by a and cos n pi y by b e to the power minus j beta z. And of course the last component is hy. This is minus plus j beta n pi over kc square b a m n cos m pi x over a and sine n pi y over b and e to the power minus j beta z. Fine. So right now we have all transverse component required here, and along with that this HC component, total 5 component, okay, for this TE mode case. Okay, so like with this component what we can do, okay, first of all, for the different mode you can plot, okay, using the MATLAB the field distribution, and you can see how it look like. Fine. So this could be assignment for you, like you can use this equation and you can plot the field or the mode, actually the mode inside the rectangular waveguide, okay, plotting this EY, EX, HX and HY. Fine. Now, so here we'll be defining this thing as TEMN. Fine. Okay, because the solution is like that actually, so the designation of the TE should be like TEMN. And in case of n and m is equal to 0, okay, I'm saying if m n is 0, can you identify what will happen? Okay, what will happen? So all transverse fields components will be 0. You see here, okay, you see here, the moment you are putting m is equal to 0 or n is equal to 0, this will be 0, it means whole 0. Same here also, 0, 0 and 0. At least one sign component is there, so it means nothing. It means that this situation TE00 is not allowed, simply. Fine. So definitely we supposed to find it out fundamental mode here, okay, where the cutoff frequency will be lowest, and above that actually the propagation will happen. Fine. Okay, so hopefully we can do these things. So before that, let me define some other parameters too. So let us talk about the phase constants, okay, and the cutoff wave number, what we defined in our previous classes as well. So if you can define here, so you can write beta mn. Okay, mn actually the indices actually 1 1 1 1 0 like that. Okay, what number you are taking, it decide the modes also. Fine. Within the T actually we have the different variations. Fine. So this is actually k square minus kc square, and this is mn. We can again designate like this. Fine. And this is k square minus, and this could be written as kx square plus ky square. Our discussion was started like this, these things. So finally, yes, you can write this kc mn is equal to under root kx square plus ky square. This is equal to m pi by a whole square n pi by b to the whole square. Finally, so finally we can write beta mn is equal k square minus m pi over a square minus n pi over b squares. Okay, so this is the phase constant. Now it is really very important to see some of the observation here. So let's say if k is greater than kcmn, fine, what will happen in this case, that the phase constant will be real in that case. So it means that we can expect here the unattenuated propagation modes. Unattenuated propagating mode. Fine. and the moment the k is less than kcmn, okay, in that case there will be no propagation, and we are calling as evanescent mode. Why? So how we can define the cutoff frequency? Simply k is equal kcmn. Okay, so this define what? The cutoff frequency. Fine. Okay, so finally you can write some equations here. Okay, how we can write? Please check. So we can write these things. kcmn is equal to under root m pi by a to whole square plus n pi by b to the whole square, and this is equal to what? 2 pi fc mn under root mu epsilon. Fine. So finally, yes, you have a formula here which is fc, the cutoff frequency, mn is equal to 1 over 2 under root mu epsilon, and of course in square root you have what? M by a to the whole square plus n by b to the whole square. That's all. Fine. So this is the cutoff frequency. Now, in a similar sense, what we did in a parallel plate system, actually, again we can write here this phase constant, wave impedance, and the guided wavelength, and of course the cutoff wave number in terms of the cutoff frequency. Okay, so yes, I can summarize here these things, writing these things like beta mn. Okay, what is that? Beta mn is the phase constant in terms of the cutoff frequency. You can see this is k times of 1 minus fc over f to the whole square. Okay, and in a similar way, okay, the outcomes may be utilized to write the wave impedance for TEMN mode as Z TEMN. This is a wave impedance, and we define K eta by beta, and yes, you can write eta upon under root 1 minus fc over f to the whole square. Fine. Another parameter is the guided wavelength. Okay, lambda g mn, which is 2 pi by beta mn, and this is lambda over under root 1 minus fc over f to the whole square. Okay, and the last one is, what is that? The lambda c mn, which is cutoff wave number. It is 2 pi over kcmn, and this is 1 over fc under root mu epsilon. That's all. Okay, so this is about actually the TE mode. Okay, and the associated parameters. Definitely these field components, what we derived was actually is very important to visualize the field components inside the waveguide. Okay, and definitely we should know the cutoff frequencies and all, and we define the wave impedance, lambda g, lambda c, all the things. Okay, I have given already the explanation in last class about those things, so you can check those things also. So for this class, this is all about, and next class we'll check the rectangular waveguide for the TM mode. Fine. So in a same way, actually one can find it out these field components as well as the associated parameters for the TM mode. And then after we'll conclude that what will happen to the cutoff frequencies and other parameters if we are in the TM mode. Okay, definitely the there actually in TM mode we supposed to find it out the EZ component, another longitudinal component, their HC will be 0. Okay, so this is all about for this class. Okay, we'll be continue the TM mode in the next class. Thank you so much.